Okay, so then the topic for the next hour is what is usually called, I think, pretty certain, it's called numerical integration. This is not integration in the sense of computing integrals, but in the sense of computing solutions to ordinary differential equations. Actually, integration. Integration. Computing integrals numerically is called quadrature. It's interesting. And why is this important? Well, the reason that this is important is that the initial value problems in the systems of ordinary differential equations, or also partial differential equations that are used in neuroscience, in computational neuroscience, and in cognitive computational neuroscience, usually are quite complex in the sense that they are made up by scientists to model some new biological phenomena, and them are usually not of the form that differential equations are that you find in textbooks that have been studied for a long time and for which people know how to find analytical solutions. So it's relatively easy to write down some initial value problem, so something like this, by coming up with some function of some n-dimensional vector x and time. And then the question is how to now find an actual trajectory of the function x that kind of is described here. And the thing is, this can be done quite readily if you have a computer, and with the computer if you have some initial value. I think actually here let's somewhat helpful or not, time is in this interval AB. Maybe I should change the notation there, but if you have an initial value here at time A, then it's relatively straightforward to do that with the help of a computer. And these are called numerical integration procedures. So Runge-Kutta is a big family of integration or numerical integration procedures that are heavily used. So if you go look into Python or MATLAB, I think the first thing that you will come across is Runge-Kutta. We are looking here at something that is simpler than Runge-Kutta, namely the so-called Euler methods. And the aim of these Euler methods is to compute solutions to initial value problems based on some recursive algorithm that you can implement in a computer. And how that works, this is what I'm trying to explain next. So, Euler method. And so what this means for you is essentially that you don't have to worry about all the analytical theory, so this cognitive thinking theory of how to solve initial value problems, but you can, once you know what an initial value problem is, what the concrete function f is, and what the concrete initial value is, you can just implement this in MATLAB and look at the results. This is what computational neuroscientists do all the time. Then they add a little bit of noise, and then they look even more. So the general idea, of course, in numerical integration is to, instead of dealing with time in uncountable sets, so in intervals that are subsets of the real line, to do something that you, of course, will find much more naturally, to look or to consider a set of support points tk. So time is not continuous anymore, but time is discrete, and there are support points tk, which we allow here to go from 0 to m. Yeah, so of course this is a little bit more natural than the continuous time, because also if you use this for data modeling, your data will also be discrete. You can of course also fit continuous things to discrete data points, but you also know that in the end everything in a computer is discrete. So whenever you have something that looks continuous, if you plot it, you also know that these are just many more values than the ones that you then label as discrete. So instead of looking at continuous time, we are now looking at discrete time. So we're looking for solutions in discrete time. That was different previously. So the exponential t, or c times the exponential t, that was continuous time. Now we're dealing with discrete time. And the way this is then typically done is then if there's interest in defining, or no, not defining, in finding a solution for an initial value problem on this interval a, b, what is usually done is that this interval is discretized into a set of support points, and so here I'm denoting this as follows. So the discrete interval is given by t0, which is defined as a, and then the next time point is t1, and then the last time point is tm, which is defined as b. So this is the support set. So what this means is, or how you can imagine that is, of course, that you have discrete time points in here. So here a is then t0, then you have t1, t2, t3, t4, t5, and t6 in this case is b. Yeah, so the continuous interval, or what we also discussed previously, that we just have the entire real line, this is now made more concrete and specified and exemplified for a fixed set of discrete support time points. And one can use these methods not only in the case that these discrete time points are equidistant, so that they have the same distance for all time points, but we will actually also leave it at that in this case. So we define an equidistance between two time points, hk, that's an h, to be tk plus 1 minus tk. So this is not necessarily that this means that this is just the distance, and it can still vary depending on k, but we assume that it doesn't vary. Yeah. So that's maybe a little bit subtle, because you would think, especially if I draw something like this, that things are equidistant anyway, but they don't have to be, but we assume that they are anyway. So the important thing here is that we denote the difference between tk plus 1, so for example between t3 and t2. This difference, so this distance here, we denote this by hk, and we can in addition assume that the hk are all the same, so that the points are equidistant, but we don't have to. Yeah. So basically, so far not much has happened. We just split up this continuous interval into a discrete set of support points. Yeah, and then the aim of these numerical integration methods is to actually approximate the value of the function that we are looking at. So the value for which we have, the function for which we have initial value problem, to approximate the values of this function at these discrete time points. And these approximations are denoted here by xk. Yeah, so don't get confused. This is the function at support point tk, and this is the approximation of x tk. Yeah. So, for example, if our x, after all, is the exponential function, and one of our tks, so for example t5, is 1, then this value here would be x 1. So that would be, maybe I shouldn't do that. That would be exactly something like the Euler number. And we try to approximate this by some other value, for example 2.9 or something, by which we approximate this. Yeah. So this is the actual function evaluated at a discrete time point, and this is the approximation. And the question is, of course, how or what to use as an approximation. Yeah. So we haven't discussed that yet, but that's the overall aim. And then the way this is typically done is by using what is known as a Taylor approximation. So who of you knows what a Taylor approximation is? Also the mathematicians? No? You know it? Have you heard it? But it's actually depends on where you do that. It's, in a way, it's analysis 1. So the way this is done, and I can can explain a Taylor approximation and this at the same time, so that doesn't hurt. So it's the Euler method actually works using a first order Taylor approximation, which takes this form. So it assumes that the function x at time tk plus 1 is given by, or is approximated by, let's say we set it like this now, by the value of the function x at tk plus the rate of change of x at time tk times the difference between tk plus 1 and tk. So maybe Taylor approximations then, briefly, because that's essentially just a Taylor approximation. So Taylor approximations basically work, let's do something like this, don't know, like follows. So Taylor approximations are local approximations of functions. So here you have now, let's say, a function f of x. So you have a function, and Taylor approximations allow you to approximate this function around what is called a development point, Entwicklungspunkt, typically denoted by A, as a Taylor series. As a Taylor series. If you stop the Taylor series at a given Taylor term. So for example, after the first order term, which is what we see above, then this is also called a Taylor approximation. And the example, so I will show you, maybe I just explain a first order Taylor approximation, because then we don't have to deal with all the rest. So the first order Taylor approximation says that the value of f at x, so x can be, for example, here, it can also be here, is approximately the value of f at a. That's quite a bad approximation, because if you are here for x, then of course your fx is up here, and this is quite different from your fa. But it also says the first order that you add to this the rate of change of f at the location a. So that would be the derivative of f at location a times the difference between x and a. Yeah. So here in this case, let's say that this is the local slope. So this is f prime a, so the derivative. And then this is a formula that says if you want to compute fx approximately, then you should take the value of f at a, so this value, and add to it the difference between x and a. So if you're going further away from a, so if you're going with your x here or further here, this difference gets larger, and you should scale this difference by the slope. Yeah. So if, for example, we have our x here, we basically just multiply the difference x minus a times the slope that we have in this point, and we'll get roughly something like this. So this will be our approximation of this here, our approximation of fx based on a first order Taylor approximation. Yeah. So Taylor approximations can go higher, so they go on essentially by looking at including second order terms and third order terms, so that you look at also the second derivative, the third derivative, and increase essentially the exponent here, and at the same time also decrease the contribution. So the biggest contribution is given by the zeros order term, then it depends a little bit, but you scale them down definitely based on these factors. So that would be the first order approximation. Only having this would be a second order approximation, which is very important in the free energy principle, because Taylor approximations are heavily used in the free energy principle for perception. So you can go on and go to increasing order, make the approximation better and better. The actual Taylor series or the Taylor's theorem specifies also something about the remaining error that you get when you do this approximation, and that this error is not larger than something. So this is, in a nutshell, the Taylor approximation theory. We only need this first order Taylor approximation here, which is here written now for the general way how things are discussed when you talk about Taylor approximations, but it's exactly the same thing here. So our A is here, our TK, that's this. And our x is here, that tk plus 1, that's this. And what this just says is that the value of x at tk plus 1 is approximated, maybe we do it after all, approximated by the value of x at tk plus the rate of change of x at the location tk multiplied by the distance between tk plus 1 and tk. Yeah. So of course this is a approximation that is only good if the distance between tk plus 1 and tk is small. So if you basically split up the interval that you're interested in quite finely, because it depends on the function. So if the function is linear, then the whole thing works well, because that's basically just what the function is about. But if you have a function that varies a lot, so it's quite nonlinear, then this approximation only works well over small distances. But there it works. So if you go to smaller and smaller distances, tk plus 1 minus tk, then you can also approximate complex functions with complex trajectories well with a first order Taylor approximation. Yeah, so that's the basic first idea of this Euler method. Are there questions about this? So do you feel you know what a Taylor approximation is now? And if not, why not? Good. So you... It's clear. Okay, good. That's good. So the idea is to use this first order Taylor approximation to find this x tk plus 1. And the good thing is that, so this is just a first order Taylor approximation, but the good thing is that we know more already. So we know, if we know tk, then we also know the value of the derivative of x at tk, because the derivative of x at tk is given by our function that describes the first order ODE or the initial value problem, because this is how this whole thing was defined. Yeah, so we started from a initial value problem here, and now if we have a fixed value tk, then we know, oops, also needs a tk of course, then we know the value here. Somehow I'm sloppy today. Then we know the value of the derivative of x at tk, because we know that from the problem. The problem was given to us as such. Yeah, so we know that, and we also defined that the difference between tk plus 1 and tk is denoted by hk. That's more notation than anything. So we can directly rewrite this approximation as follows. Let's get rid of that. So this is the first order Taylor approximation, and then we can rewrite this as x tk plus hk f tk x tk. Well, and how this function f maps a tk and an x evaluated at tk to a value x dot tk we know from the setup, and this is actually the function that if you use this in an actual programming context that you would have to implement. Yeah, so you would have to write a function that implements the evolution of the system, so that takes as inputs, I mean this is just repeat, but it takes as inputs time and the values of x, and gives you as output a value of x prime. Yeah, so x dot. So this is actually the thing that if you do do this in real data analysis or real programming, this is what you have to program. And that's relatively straightforward because you're given this function explicitly with your initial value problem. Yeah, so far so good. So this is now almost already an algorithm, except for two things. So first of all, the question is how to start this. And to start this is relatively straightforward because we said that we know our value t0, because that's, we now call it a, and we also know the value of x at t0 because that's our x0. Yeah, so we can actually for the first time point, which is indexed with 0, we can put something in here because we have our xt0 and we have our t0. Yeah. Now, if we put something in there, and also here we have our xt0. So we know our hk, we have our xt0, and we can evaluate this. Then, of course, we can immediately evaluate our x1. So maybe I write it out. So yeah, I'm just writing it out here. X1 is our x0 plus hk times ft0 x0. Yeah. So t0 we know, x0 we know. That's our x at t0, and we get now an approximation. So there are two ways you can look at this, either like this or as this. Yeah, so we approximate the value of the function x at t1 by taking our initial value and adding to it the multiple of our distance between our discrete sample points times our function that we know evaluated for t0 that we know and x0 that we know. This value we don't know, but we approximate it now. And then the final trick of the Euler method is to say, okay, this our xt1, which we approximate here, this we now call x1 and use it in the next step, because for the next step we need x2. Then if we have our x1 and our xt1 is approximated by that, then of course we can, this could also be a 0, then we get this. And in this way we can go on. So the general way that the Euler method then of course works is as follows. So xk plus 1 is given by xk plus hk ft1 x1. Sorry, k. I'm sloppy today. So that's then essentially the recursive algorithm. So maybe one should start it with an initial condition. So 1 set x0 to be our how do we call it? We call it xa or whatever. So define our x0 as the initial value, and then for k going from 0 to m minus 1, compute the xk plus 1 according to this, and you always have the lower k here because you've just computed it, and then yeah, you get a list of numbers. So you get a list of x1, x2 to xm, which are the values that you assume for your t0 you've been given, and then your t1 to tm. Yeah, and you compute them based on this algorithm. So let me show you a picture, and then we can also talk questions about this. So this shows 4 things. So one thing is that it shows our 2 exponential of t function from our initial value problem. Yeah, thanks. I don't want to say them. So it's in black, and it's the one without the dots. So let's make this bigger. So there are 4 curves, and one has no dots in it. That's the actual function. So that's yt 2xt. And then I evaluated this here on the interval 0 to 2 and used varying numbers of support points m. So in blue I used 20 support points. So you can see this blue thing here where the approximated values are relatively sparse compared to the other one, and you see also that the error compared to the true solution is definitely larger than the other ones, which used more support points. So the red one has 50 support points and the yellow one has 100 support points. So you see that there are more beats on these strings, if you want, and you see that the error with respect to the true function gets lower. And what you also see is that in the beginning, but that's how it is here, in the beginning they are actually all quite well, but as you get larger, the error increases. And that's just based on the Euler method. And of course, the Euler method is not the one that is typically used. Typically, Rohn-Cotter methods are used, which are more complex but better. So Euler methods also, at least in this case, work quite okay-ish. Well, questions about the Euler method? Do you want to see a programming example? Should I now program that and then you would be happy? Or okay, good. Then I do that. The other thing would be to look at the modified Euler method, which uses a little bit different, but I think the programming is also fine because this is really a programming issue. So let's have a look. I'll rechange it. Why didn't you change it? Good, so the initial value problem, maybe let's look at the other one, because if you again look at the exponential function, we all go to fall asleep. So, but there I don't know no, well, let's look at it anyway. Is it good? Let's see what happens, whatever. I have no idea. Does anyone know the analytical solution to this other thing there, this x squared minus t? I don't know. But we can at least see, do I know some other nice solution? No, anyway, doesn't matter. Good. So then let's first define some time interval. So time, usually I call this minimum of time. So that's the lower boundary, and maximum of time. That's the upper boundary, and then use MATLAB's linspace to get a number of values in this interval, usually some res. So let's say 1, 1. See whether now everything crashes again because I'm recording and doing MATLAB at the same time. No. So these are now our support points. Maybe I call them TK to make that even clearer. So these are our TKs now. So 0 to but let's close this at least. To be safe, and I also close this. Not that the recording stops again. So these are now our support points, and then if we want to use the Euler method, we of course also need some initial values. Let's do some things here. So these are our support points. Before we look at the initial values, let's just define our HK as the differences between the TK, although this would maybe not, maybe. So you see that linspace uses equally spaced time points TK, so the difference is always in this case 0.2222. Of course, that depends on what we use here. If we use 20, then we have different, but the distance is always the same. So let's comment a little bit here. Lower interval boundary. Upper interval boundary. Interval, discrete interval. These are then our support points. And this is our, they also called increments, or distances between the TK. And then let's specify initial value. So t, how do we do that? Maybe let's do it like this, t0. No, let's just define the x0. So we take as t0, we take our first tk in here, and as our x0 we take I now want to reproduce what I have there in the script, so this is why we now take the initial value to be minus 1.5, the initial time point, and then we take minus 0.8 as the initial value. Now the crucial thing about, as I said, the crucial thing in terms of programming Euler methods or Runge-Kutta methods or anything is to write a function that implements this slope field or the slope field or the evolution function, however you want to call it. And for this we do a new function here, and we call that the f-fun, which takes in some argument t and some argument x, and returns some argument x dot. Yeah, so this is the function ftx, which returns the rate of change at x. Yeah, n, but n is also one here, n-dimensional function value. So and as I said, I'm looking at this other example here. So there the output argument was defined as x square minus t. Yeah? And that's it. So this function doesn't have to do anything else. I'm always a little bit split between calling the output argument actually something like this or calling it f evaluated at tx, but I think for this moment it's fine. So we should now be able to call this function for example, for our input, for our initial value. So let's do an example here. X dot 0, something like this, is our tk1 and x0, just to see whether we can call it and everything works. We're missing an end. So we get 4.7, which looks a little bit like, it's definitely positive what I have on this plot there. Now, that's good. So we now can return things based on this function. And now it's essentially, the final thing is to implement this recursive algorithm. And then it always helps to, if you're programming something, to clarify the math first and then do the programming. So specifically, it implements the recursion. Let's write it down. X k plus 1 is xk plus hk times f t k x k. So, and then one way I tend to do this is to initialize the array. So this. And let's initialize this. So initialize it to none. For of course, we want one value of our function that we're trying to evaluate here for each value of the tk. So it should have the same number of points. So that would be this. Function approximation initialization or something like this. So that tk and xk are fine. And then we can now implement the Euler algorithm. So first thing is initial condition initialization. So xk at 1, and this is the thing with MATLAB. MATLAB always starts from 1. If you would be using Python, you would have 0 there now, which is more in line with what most of the textbooks do, because they are usually inspired by C or other programming languages which start with 0. But yeah, that's how it is. What can one do? One can write, for example, the text starting at 1. And we should set that to x0. Yeah. And then we do the recursion, and we do that simply as a for loop for k going, how do I do it here, with +1. So we start from 1 and go to, actually we couldn't call our t-res here, we can call that m because it's called m all the time. I could have had simpler. Now we just need to be very careful because our hk is of a different size, but then we can have our hk at k plus 1. So it starts, k starts with 1 here, and now we're adding something, so we get to 2 equals our xk at k plus our hk at k times, and now this is why we wrote this function, f fun times the time point tk. Maybe we call them just t, then we don't have that many k's there. A little bit easier to see. So now it looks a little bit more like it does here. So xk plus 1 equals xk plus hk times fun, time at k and x at k. So basically, and this is always important when you write these recursive loops, on the right side we only have things with k being k, and on the left we have k plus 1. There might be a thing that this index crashes, but it doesn't. So this is what we got returned. So let's plot this. So let's plot tx, maybe with some dots. Sample plot. So if you look, compare that to, this is actually in the script, it's actually squared. Well, that doesn't look too bad. The problem is that we now cannot really do much in terms of comparing that to the analytical solution, because I don't have the analytical solution with me. So we can only, for example, increase the number of support points and look at it. The thing is, if you do this, so this is now how it looks for many support points. If you do this in, that's not squared, then we can see a little more. If you do this in actual data analysis, for example, using the integration that SPM gives you for dynamic causal models and so on, then there's also no analytical solution. So in a way, you just get solutions then, and have to be happy and hope that they are okay. But that's essentially it, and I've almost filled an hour with this. So this is essentially what this means, and this is actually also how it works then in data analysis in DCM and in neuroscience in general. So instead of trying to find analytical solutions by studying a lot the theory of ordinary differential equations, one gets away with this kind of recursive algorithms that one applies, of course, now not for evolution functions and systems as simple as this, but then also not necessarily more complicated ones. Well, they are more complicated, but not that much. So, for example, for the DCM model, it's 5 state variables, and it's not that complex. For the magnetic resonance imaging, which we will see after the Christmas break, it's 3 state variables, so it's also not more complex. But if you, for example, look at the EEG models, then things get more complex in terms of the number of state variables. So we have a paper from 2016 with Ludger Starke on delay differential equation modeling, which basically uses this whole thing in a proper statistical inference framework, namely variational base, much like DCM for ERPs, but looks a little bit closer at the underlying math. So if you're interested in this, have a look. It's also the free energy principle. Everything is the free energy principle. Yeah, questions about this? No. Good. Then we're actually done with our introduction to differential equations and ordinary initial value problems. So the next thing then after Christmas in neurocognitive methods is to look at the initial value problem that is at the center of magnetic resonance imaging, which then leads to the solutions which are known as precession. So we will apply this theory immediately after Christmas for magnetic resonance imaging. Good. Then let's have a break and at 10 start with statistical methods.